So my name is Benjamin Lilienthal-Uhlich. I'm head of the business unit Next Generation Computing at Fraunhofer IPMS, and there I'm coordinating all the quantum computing activities in our institute. In QSolid we are two Fraunhofer institutes, so the IPMS and the IZM ASIT, and both of us are traditional semiconductor fabrication or microelectronics institutes. So we don't have a long-standing experience on fundamental quantum physics, but as usual for Fraunhofer we present more the applied research part of research and development. So our goal in principle is to not look at the fundamental science part, but really at fabrication, bringing everything into the industry. So maybe for later parts of the whole quantum computing activities. So formally we are integrated in Work Package 5, that means hardware or technology for hardware integration. So the goal here, or as a principal goal in QSolid, it is to priority one, improve the quality of qubits, but also look at scalable solutions. So in the end, it's probably commonly known that for really useful quantum algorithms and applications, we need 1,000 or millions of qubits, and we need very good qubits. So the idea is we use all the experience and the modern semiconductor manufacturing industry, because they've made tremendous advantages over the last 60 years. You just have to look at your modern microelectronics, like in a smartphone, there's a small chip and billions of perfectly manufactured transistors are on it. So the idea is really to leverage these infrastructure and the competencies of the microelectronics world for quantum computing. So we are there to really develop scalable solutions. So we would come at a later stage of the whole quantum computing regime. So because it's of course important to have a demonstrator and to show in the lab that it's working. But in the end you have to fabricate everything, and you have to move into industry, and you have to develop processes and use materials which are commonly for the industry. So that's the overall goal of Fraunhofer. And maybe as another motivation, right now, especially for superconducting qubits, you all know the typical picture of the huge cryostats and the dilution refrigerators you need to just cool down everything to millikelvin range. So there you have the problem, you just have a tiny chip which is cooled to millikelvin, but you need for every qubit discrete basically RF cables which go out for initialization, manipulating and reading out the qubits. So this works very good if you have 100 qubits maybe at most, but it will not be feasible if you move to 1,000 or more qubits. So you simply cannot have more than 3,000 lines going out of it. And that's where an integrated solution is needed. So the overall topic we are working on in the whole Work Package 5, together with partners from Jülich, of course, and GlobalFoundries, is to co-integrate a CMOS control logic and a QPU. So the vision basically is to put everything on a common substrate, put it in the fridge, and then have an integrated solution for everything. And then you don't need a discrete cabling, which will not work beyond 1,000 qubits. So that's our principal goal. So the control logic will come from GlobalFoundries. And one of our two tasks in the project is to see if this traditional CMOS control logic, which is right now used for everything in daily life, how this will work at low temperatures, because it's not really known how this will behave. And also how can this be co-integrated with a quantum chip. So the other part, which we are working together with the other Fraunhofer Institute and also GlobalFoundries, is to develop some technologies to put everything together and see if this works. So it will take a while, but it's a very interesting concept. Maybe one technical challenge is really, let's call it heat management. So if this approach works, then you have basically a CMOS control chip and a QPU next to each other. And these are technologies which come from different parts basically. So the CMOS control chip needs to work at low temperature, but it also basically generates heat, which we don't want on the quantum chip. So we need to think about strategies to mitigate heat transfer, but still have the electrical connection. So this is a technological challenge. So the QPU does not want to get warm, and maybe the CMOS does not want to get cold. And maybe as far as non-technical challenges, it's an interdisciplinary work here. So we have to connect from different fields of science, and yeah, oftentimes it's a little bit hard to really put together the physicists and the engineers, because inherently they maybe not speak different languages, but yeah, different dialects maybe. So this is challenging, but also interesting to put those people together. I guess one good result is that we actually have the people working on QSolid, because that's a big problem right now in the industry, but also in the whole of science, to get qualified people quickly on board. We obtained our first cryogenic characterization equipment. This is very good, and we have the first initial result that it really works at a low temperature. And maybe another achievement is that we now have a common understanding of a design for this co-integration of QPU and CMOS control chips. So the design is thought after. We know which party has to do what. And maybe another good result is that we have aligned on the materials we want to use for this thermal management. So we are pretty confident. Of course, the first months are always a little bit slow in the project, but we are happy with the progress so far.